Greetings, differential equation fans. This is the first video on higher order differential equations. A big theme in this chapter is the study of the second order differential equation, ax double prime plus bx prime plus cx equals f of t, which is initially motivated by Newton's second law. We'll see that there are a lot of adjectives to describe this differential equation. It's linear. It has constant coefficients. Here A, B, and C are constant. We refer to it as constant coefficients. It's second order, and in this particular case, it happens to be non-homogeneous. Okay, so those are terms that will come up again a little bit later. For the time being, though, we'll think about this in terms of Newton's second law. So we'll first derive a couple differential equations of this form, again motivated by a mechanical system, namely a mass spring system. We'll see then how to draw analogies to that mass spring system with a different system, with an electrical system, and then we'll talk about some energy considerations of this system. Okay, so without further ado, let's go ahead and talk about spring motion. So here is part one of spring motion. We'll assume that we have a mass m on the end of a spring, which is characterized by a spring constant k, and we'll go ahead and define x of t to be the distance that this mass is from its equilibrium position. So you can imagine that there's a preferred length that this spring takes, and if we pull this mass out to a distance non-zero away from its equilibrium position, or give it a push to get it going from equilibrium position, or maybe even both, you could imagine that this mass is going to bounce around, and we'll call that unknown function x of t. That'll describe the distance the spring is from equilibrium. Okay, so more about this spring constant k. We'll assume that the spring exerts a resistive force proportional to the distance from equilibrium. This is better known as Hooke's law, that force is proportional to the distance from equilibrium. So we'll go ahead and use Newton's second law to derive a differential equation for that. Again, Newton's second law is that the mass times the acceleration is equal to the sum of the forces on the spring. And in this case, we'll take mass times acceleration to be mass times the second derivative of the position function. And in this case, we'll just think about one force acting on this spring, namely that the spring force, which again is opposite to the position, right? If the position is positive to the right, the spring wants to pull the mass back to the left. And similarly, if the position is negative to the left of equilibrium, then the spring wants to push it to the right. So our F sub s is negative kx. Okay, so applying Newton's second law, we see that a perfectly good second order differential equation for this unknown position function is mx double prime is equal to minus kx. Now we'll write that in a little bit different format here, moving the kx to the left-hand side of the equation, and restate our problem as an initial value problem by appending an initial position, call that x naught, and an initial velocity, call that v naught. So as you might imagine, with a second order differential equation, we have to specify both the initial position and the initial velocity to formulate the problem correctly, and we can see that here. Okay, so in the special case where v naught is 0, we can verify that x of t of the form x naught equal cosine omega t is a solution. So to do that, we'll just plug in this form of the function x by having a look at the second derivative here, which is minus x naught omega squared times cosine omega t. And when you plug this in, mx double prime plus kx, we can reorganize and factor out the x naught and factor out the cosine term, and we can see that this function is a solution, namely mx double prime plus kx is equal to 0 if omega squared is k over m. And we'll see soon where that comes from. That comes from a relationship between the mass and the spring constant that actually comes out of the differential equation. So we'll be able to derive that soon. Certainly x of 0 is x naught, and if you take the derivative of a cosine function, you'll end up with a sine function which evaluated at 0 also gives you 0, so that the solution satisfies the initial values too. Okay, and again, we don't yet know how to find the solution. We'll see that soon, so just hold on till our next section for that. Here is a graph of a solution of the form x naught cosine omega t for specially chosen values of m and k that we'll see how to identify a little bit later. Okay, a second flavor of these mass spring motion problems is called damped spring motion. So in this scenario, we'll go ahead and think about a mass m on the end of a spring, again defined by constant k. And we'll add into this a damping or a dash spot that'll be characterized by a constant gamma. Once again, we'll go ahead and think about letting x of t represent the distance that the mass is from equilibrium. And for this damped force or frictional force, we'll assume that there's a resistive force that's just proportional to the velocity. So again, we can use Newton's second law to derive a differential equation model for this damped spring motion, where ma is equal to the sum of the forces. And again, we'll take ma to be mx double prime. And here we'll think about two forces, namely the spring force that we had before, as well as the resistive force, F sub r equals minus gamma x prime. And again, just a quick sign check here. If our mass is moving to the right, we expect x prime to be positive, so that the resistive force should be to the left. And similarly, if the mass is moving to the left, its derivative, x prime, or its velocity is negative, so we would expect the resistive force to be to the right, or a positive number. So here's a perfectly good differential equation, a second order differential equation again, for the position function, the unknown function x of t, just by applying Newton's second law, mx double prime is equal to minus kx minus gamma x prime. Once again, like we did with our last differential equation, for this differential equation describing damped spring motion, we'll go ahead and move the gamma x prime term and the kx term to the left-hand side of the equation, giving us again a constant coefficient, second order, homogeneous differential equation, together with some initial conditions here. X of 0 is x naught, and x prime of 0 is v naught. A perfectly well-formed initial value problem. So it turns out that solutions of this system are rather complicated, and they depend on particular relationships between m and gamma and k that we'll be able to unfold soon. But for the time being, I want to suggest that some solutions of this system have the form x of t equals some constant times an exponential, a decaying exponential, times sine of some value omega 1 here. I've called it t. So we'll see that functions like this come up quite a bit, and they actually have form, or the graph of these functions is sort of this oscillation that decays over time. So you can think about the dashed lines as what we'll refer to as the envelope of solutions, which is a times e to the minus ct, and you can think about the blue lines as the actual solution, which it's convenient to consider to be maybe a time-dependent amplitude that decays over time times some oscillatory function. So you can see how this function oscillates with some pseudo period defined by omega 1, and then decays over time. So again, we'll see more on how to find this solution a little bit later, but just wanted to introduce those couple of terms, envelope of solutions, and then this decaying oscillation in the case of a damped spring motion. Okay, so it turns out that this mechanical system, the mass spring system, is in analogy to our RLC circuit from previously. So to see that, I'll remind you of the differential equation in the case of an RLC circuit. We'll go ahead and think about the law that gives us a second order equation, which is Kirchhoff's voltage law, saying that the voltage drop, the sum of the voltage drops around the circuit element has to be the same as the voltage supplied by E of t. And once again, just a few other laws here. Ohm's law tells us that the voltage drop across a resistor is IR, and then the capacitor and the inductor, defined by C and L, have similar voltage relationships with the current, the derivative of the current actually in the charge. Okay, so we saw how this relationship, Kirchhoff's voltage law, gives us the second order equation for Q, which is L Q double prime plus R Q prime plus 1 over C Q is equal to the voltage supplied. So in the special case where that voltage is constant, we can just differentiate that equation to identify a similar constant coefficient, second order, homogeneous differential equation for the current now, which is defined by I of t. Okay, so again, in this scenario, the current is an unknown function, and we'll see that the current and the different circuit elements are in analogy to the distance from equilibrium in the spring and the circuit and the elements of that system as well. Okay, so here are those two differential equations side by side, and we can sort of think of the spring and the capacitor as ability of the system to store energy. So just like one would charge up a capacitor, one can think about compressing a spring to store energy. Similarly, gamma and R describe energy dissipation. So a resistor as well as a frictional force both describe how energy is taken from the system. We'll see that more clearly in just a second. And then finally, in some sense, the mass and the inductor, described by their constants M and L, describe inertia of the system. Okay, so there's a pretty big parallel between the mechanical and the electrical systems that we've been talking about. Okay, finally, we'll go ahead and think about our mass spring system in terms of energy considerations. So this is motivated by the observation that mx double prime plus gamma x prime plus kx comes from Newton's second law, right? This is mass times acceleration equals the sum of the forces. In other words, every term in that equation is a force. Okay, so it turns out if you multiply a force by velocity or by meters per second, multiplying newtons by meters per second, it ends up giving us a unit of energy per time. So to see that in this case, we'll go ahead and write m x prime x double prime plus gamma x prime squared plus kx x prime equals 0. And that differential equation can be rewritten as the derivative of 1/2 m x prime squared plus gamma times x prime squared plus the derivative of 1/2 kx squared is equal to 0. And just go ahead and use a chain rule, and you can work from these derivatives back to m x prime x double prime and kx x prime respectively. Okay, so those quantities should be probably a little bit familiar to you. If you think about x prime as the velocity, 1/2 m velocity squared is a kinetic energy, and similarly for a spring, 1/2 kx squared turns out to represent potential energy. So those two terms end up being time derivatives of kinetic and potential energy respectively. So to see how to think about this system with a full energy consideration, we'll go ahead and write that sum of derivatives as a single derivative of a sum and move the dissipation term, or the gamma x prime squared term, to the right-hand side of the equation. So when you do that, you see that the time derivative of the sum of the kinetic plus the potential energy is equal to minus gamma x prime squared. Or in other words, the rate at which total energy in the system changes is equal to negative gamma times the derivative of the velocity squared. Now, the term on the right-hand side for non-zero gamma is always negative, which tells us that the total amount of energy in the system is decreasing, or in other words, that that frictional term defined by the constant gamma works to dissipate energy. Now, in the special case where gamma is equal to 0, or where there's no damping in the system, we see that the time derivative of the kinetic plus the potential energy is equal to 0, so that sum is constant. And this is a classical conservation of energy law that occurs when in this case we have no dissipation in the system. So in the special case where gamma is equal to 0, all of the energy in the system is either in the kinetic energy or the potential energy, and as we'll see soon, it actually goes back and forth between the two. Okay, hope you have enjoyed this video on an introduction to second order systems. In our next video, we're going to have a look at finding solutions of these systems and also solving some of these mass spring problems in terms of those solutions. So long for now. We'll see you next time. Bye-bye.